get started, there's a handout coming up which has some little tables and matrices which may prove a little helpful because you wouldn't want to have to copy this stuff down. Today we're going to look at this idea of public goods and the prisoner's dilemma a little bit more. Talk about the voluntary contributions mechanism. Then we'll see in the simultaneous type of games, there's a certain type of reasoning process that you go through. And the thing about the simultaneous games, of course, is that you can't observe what other players are doing. Neither player can. So they basically have to think. And part of the thinking process is to try to figure out, do you have a dominant strategy? Does the other player have a dominant strategy? Okay. And the concept of the dominant strategy is kind of a neat idea, because normally in games and strategic interaction, you have to try and figure out what the other guy's going to do, what the other players are going to do. And so they might do this, they might do that. You're not really sure what they're going to do. You know, you might be able to think about it and narrow it down. But if you have a dominant strategy, it doesn't matter what the other players do. It's the best, no matter what they do. Okay, so that's kind of a cool idea to think about when you're. If you can find something for yourself that doesn't matter what you believe about what other people are doing, it's always going to be this thing's the best to do, then that's the reasonable prediction for what you'll do, okay? And vice versa for the other player. If they've got dominant strategies, that is, strategies which are best for them no matter what you're doing, you can expect them to play those kind of strategies. And then you put the two together, and that's called a dominant strategy equilibrium, if such a thing exists, okay? Now, we'll find games where there aren't dominant strategies. The prisoner's dilemma happens to be one where both players have dominant strategies. Okay, and the prediction or the equilibrium idea that comes out of the prisoner's dilemma is a pair of strategies and some payoffs from those strategies, where both players are playing their dominant strategies. Okay, now it turns out with the prisoner's dilemma that there are other things that aren't dominant strategies that if the players did them, would actually give them both better playoffs. And that's why it's a bit of a dilemma. It's sort of saying, well, gee, what seems to be individually rational, sensible things to do, best for me, best for you, isn't that best for both of us? Well, funny, no, there's something that's actually better for both of us, but we didn't get there with our way of thinking about this strategic interaction. So that's why the prisoner's dilemma is quite an intriguing concept. Now, so that'll get us, I want to get back to, we're going to go through these three ideas here. The voluntary contribution mechanism is just a way of getting a handle on a nice example of how people could actually help other people, but at the end of the day, it doesn't look like a strategically sensible thing to do. You get into this prisoner's dilemma idea, okay? There's a particular type of reasoning, the dominance reasoning, which you want to look at, just a little subtlety. It'll take us a couple minutes. I want to go back to this general structure of the prisoner's dilemma 2x2 game with the sucker payoffs and the temptation payoffs. And what is it that gives rise to this? Because do we always get it? Morgan, who isn't here today, was asking yesterday, well, do you always get this situation where, you know, when both people are doing the best things for them, there's other things they could have done if they could have done together, make them both better off? And the answer is no. Okay, we'll have a little quick look at that. Then we want to look at games where there aren't dominant strategies for both players. So we'll have a 2x2 game, but have a dominant strategy for one player but not another player. And then we'll come to games where there aren't dominant strategies for either players, but there's another way we can think about this that kind of makes sense is if players don't have dominant strategies, which is what you'd expect them to do they have other things that are dominated, that you wouldn't expect them to do. Okay, so it's kind of like sometimes when you're looking at a strategic interaction situation, you're trying to figure out, okay, what am I going to do? What's the other guy going to do? You think, well, what's the best? And you can't really isolate anything that's best, but maybe what's the worst? Okay, what are things if you did them would look pretty silly in comparison to other things you've got? Those are dominated strategies, and you might think, well, I don't expect those to happen. So sometimes when you're figuring out what to expect to happen, maybe you can't do that, but you might be able to figure out what to not expect to happen. Okay, and you eliminate some of those things, and then you might be able to get somewhere just by that kind of process of eliminating things you don't look very good. Could we get any farther? And yes, you can. In some games. Okay, and that's going to get us to probably the end of the lecture. Now, there is an exam coming up in a week, Thursday. We'll definitely cover all the material in Chapter 4. We won't get there today. Next Monday, we'll be looking at coordination games, little simple 2x2 coordination games. Again, very kind of fundamental strategic idea is, even only between two players and very simple simultaneous games, is could you get your actions coordinated to get mutually beneficial payoffs, or are they going to be uncoordinated, okay? And there's a whole series of stylized 2x2 games which you need to know. There's the Prisoner's Dilemma one we're looking at. There's the Assurance game. There's the Battle of the Sexes. There's a game of chicken. And it's just, you want to know these little stylized games because each of them has a strategic point that we're trying to take out of them, okay? So that's where we'll get to next Monday, and that'll be roughly where the exam goes up to. You could start reading in Chapter 5 for next week. Chapter 5 takes a deeper look at the Nash equilibrium concept, and we probably won't hit that till Tuesday next week, okay? And maybe Monday, but I doubt that that's going to be on the exam, but definitely Chapter 2, 3, and 4, okay? Also, I did send an email around. Did everybody get that this morning? Anybody check their emails? Megan, did you? So it was just where to go to find past exams, okay? The last couple of years' exams, I have put out answers for them, so you can look at them, kind of see my reasoning, and that should help you in your studying for the exam. There's some of the previous exams that don't have answers for them. People have asked me, would you prepare answers? And the answer to that is, no, not right now. It's actually quite time-consuming to prepare detailed answers. I started to do that more each year, but it's also a good idea for you to have some questions. Hey, they don't have answers, so how would I work them out? You know, if you can work them out, and they're not that hard, I don't think, okay? The midterm usually is a pretty straightforward exam. I think the last couple of years, the final has been a bit too hard, but the midterm generally has been pretty straightforward, okay? So you'll get an idea by looking at past midterms what the types of questions are, and even though some of them don't have the answers to them, I think you'll be able to figure out how to do it. And if you can't, then come along to those sessions next week. Okay? Now, I've given you a handout on this voluntary contributions game. Let me just go over it again. It's a two-player game. What can each players do? Well, yesterday when we had the interaction between the players, we had them either an endowment of 4 10-cent pieces or an endowment of 4 chocolate bars. They could contribute some of that endowment, or in this case all of it, to what we call a group investment account, okay? So you could give it away, and then there's an investment opportunity which was to increase the whole group account by 50%, okay? If you keep it in your private account, you don't get that big rate of return, but if you give it to the group, you can. The only problem is you have to share equally everything that comes out of the group, okay? It's a simultaneous game. We're just doing it once. We weren't repeating it. It's complete information. Everybody knows everything they need to know about the game, and nobody can communicate with one another or make any enforceable agreements. Okay. Now, the hard part in this game is figuring out the payoffs. So I left you with a little homework question, which was, what if people could give, instead of all or none, they could give some? And so I want to walk you through the construction of this payoff matrix. Okay. Now, you'll see it'll take us about 10 minutes to actually go through this in class. So you're sort of anticipating, is Fountain going to ask me a question? Like, this is a strategic interaction situation, okay? I'm trying to think, what do these students know or not know, okay? And you're trying to think, what's he going to ask me in the exam? Well, one thing you might do is think, it's going to take us 10 minutes to walk through this payoff matrix. Does he really want to spend 10 minutes in a 2-hour exam asking me to construct a detailed 5x5 payoff matrix? Probably not. Okay. On the other hand, once you step through the reasoning in this, if I'd asked you to, you'd be able to do it pretty quickly. And if you hadn't stepped through the reasoning in it and I asked you to, then it would be a pain in the butt because it's really hard to crunch through the numbers and get them right under pressure on an exam. So let's just go through this table and have a look at this game where now we've modified it only by saying there's more things the players can do. Okay, the red player, the way I've set it up here is what you keep. Okay, you might have set it up as what do you give to the group account. But so the idea here is the red player could keep all 4 of their endowment, 10-cent pieces, chocolate bars. They could keep all 3. They could keep 2. They could keep 1, or they could keep none. Or you could say, well, they give none, they give 1, they give 2, they give 3, they give 4. Okay, so the idea, these strategies here along in the rows are how much they keep for themselves, or implicitly how much they give to the group account. Similarly with the blue player. Blue player could keep 4, keep 3, keep 2, keep 1, keep 0, or they can give none, give 1, give 2, give 3, give 4. Okay? So that's their strategies. And the way we look at these, we put them in this payoff matrix framework, and we'd say, well, what happens to each player according to the various strategies they play? So let's look at the blue player keeping all 4 of their chocolate bars, all 4 of their 10-cent pieces. That's in their endowment. And the red player keeping 4, keeping 3, keeping 2, keeping 1, keeping 0. Okay? So if they both keep 4, then nothing goes into the group account. Okay? So you just keep what your payoffs are, what you've kept, 4 and 4. But now suppose the red player gives 1 chocolate bar away, or 1 10-cent piece, okay, or $1, okay? Then what's going to happen is that $1 is going to go up to $1.50. That 1 chocolate bar is going to go up to 1.5. Okay, that 1 10-cent piece is going to go up to 15 cents. So what you can think of is the group account is now going to increase, but it's only increasing because the red player has put $1 in. The blue player hasn't put any in. Okay, so then it gets split between the two of them. Okay, so that's where the blue player's payoff goes up by 75 cents. Okay, let's imagine it being $1 rather than the 10-cent piece. Okay, so we've got the blue player getting an extra 75 cents. The red player also gets back 75 cents from the group account, but they put $1 in. The red player gets 75 cents back because the group account, they put $1 in, it went up to $1.50, but they have to split it equally, so they only get 75 cents back. So they lose 25 cents on that. So that's why this number is 25 cents less than that one. Okay, let's keep marching down this column. Supposing the red player keeps 2 and puts 2 in. $2 goes in, gets matched 50%, goes up to $3. Divide by 2 is $1.50 each. Okay, so the blue player now has $1.50 more than he had at the beginning because he's getting stuff from the group account. The red player is getting $1.50 back, but they put $2 in. Okay, so they lose 50 cents. So each time as we march down this row, the red player is losing 25 cents, and the blue player is going up 75 cents. That makes sense? You see that pattern? And you know, you can work out all of the cells in the table. Let's try the second row, okay? See how this works with the second row. Now, we're thinking of second column. We're thinking of the blue player keeping 3. Okay, that means he's putting 1 in the group account. Okay, so the blue player's kept 3. There's 1 in the group account. The red player, if they keep all 4, they get half of the group account, which is now multiplied up to $1.50. So they get the 75 cents, 4.75. The blue player goes down 25 cents. So this cell here is just compares to that one over there. Okay, it's sort of a symmetric situation. One of the players, in this case, the blue player is contributing. Over here, the red player is contributing. Blue player contributing 1 into the group account, gets multiplied up to $1.50, gets split in 2, and so it's going to cost the blue player 25 cents, but the red player is going to get the other 75 cents. Now, this is, okay, for each cell, as you go from cell to cell, there's a certain pattern that emerges. And the pattern is like this. One of the players can decide to put a unit into the group account. Okay, and you can think of that as the private cost of giving to the group, okay, or getting this multiplied return. So that's $1. Okay. Now what's happening is that $1 goes into the group account, and the group account, everybody gets that. Okay. Now you imagine this is a 2-player game. Supposing we were playing in this situation here, where the group account was such: if I gave away $1. Every one of you and me, okay, would get what goes into the group account, my $1, plus multiplied by $1.50. Okay, it has to be split equally. Not very good, right? because if that $1.50 that's in that group account is going to be split equally by all you, it's going to be way down. But suppose it's one of those kind of things where when that $1.50 goes in there, you know, when I contribute $1, I'm contributing $1.50. It's Steve, right? Jason. When I contribute $1.50, I contribute $1. It's going to go up 50 cents, and Jason's going to get that, and Megan's going to get that, and everybody else is going to get that. Okay, so in some sense, it's going to cost me to give to you guys. I'm not going to get back very much, but I could get I can think, wow, I could actually give to a lot of other people. Small cost to myself. Okay, I'm only going to get back something. So that's why this game is kind of interesting. When you're looking at it from the individual's perspective, what are their payoffs? Is it just my own money? Or maybe my payoffs are to give, just small cost to me, I can get a big return to everybody else, equal. So we've only got a two-player game, and what the blue player can do or the red player can do by giving one away is at a small cost to themselves, get 75 cents in the hand of another person. And if there's lots of other people and they had a kind of investment account where that happened, now you think, well, what kind of stuff happens like that? If I put $1 out there, doesn't it have to get split equally between you? Yes, it does. But what if I put the money towards a park? Okay. So it's like $1 or $1 million goes to build an extra park, but everybody gets to enjoy the park, right? It costs me $1. And I get to enjoy the park. There's some private benefit for me, but I'm also creating all these other benefits for you. The park that I create is I can use it, you can use it. Now, again, parks get congested and stuff like that, but forgetting about that, that's the kind of idea we have here, is that maybe the payoffs in that group account are these what we call public goods, where everybody gets to experience them equally, even only when one person contributes, they have to face the full cost. So let's march down the column, okay? So we start at the top. Why is red at 475? Because the blue players put $1 in. There's $1.50 in there. It gets split equally. Each of them gets 75 cents back. But the blue player also put $1 in, so they're going down 25 relative to this. And the red player is going up 475. Let's move down the column here, okay? Now, what's happening is the red player is putting another $1 in. Okay, so in this cell, blue players kept 3, red players kept 3. There are $2 in the group account. Group account goes to 3 divided by 2 is $1.50. Okay, so each player gets $1.50 out of the group account plus what they kept, $4.50 and $4.50. Okay. What if the red player decided to keep 2 and put 2 in himself? So in this cell here, there's 2 from the red player, 1 from the blue player. It's 3 in the group account. Multiply it by 50%. That's another $1.50. So that makes it up to, is that right? 3, 450, 225 each. That sound right? You follow my logic in that? Jason, are you following that? Or is it too fast? You got that? Megan, do you follow? Okay. So, each cell you can figure out what's in the group account. Well, there's 3 in the group account. Goes up to 450. Split it at 225. 2 plus 225 is 425. 3 plus 225 is 525. Okay. So as we go down, notice what happens. The red player is giving more and more. Costs them 25 cents each time they give more in net. Meanwhile, they're adding to the payoffs of the other player in the game, going up 75 cents. And that's what every other column that I've put on that matrix has that property. Okay. Let's just pick one at random here. Okay, we're sort of saying, let's take this guy up here. Red player kept 4. So he doesn't put any in the account. Blue player keeps 1, is putting 3 in the account, goes up to 450. Split it 225, 625 for the red player, 1 plus 225, 325 for the blue player. Now as we march down, the red player is costing him 25 cents. Meanwhile, the blue player is going up 75 cents as we go down. Every column is the same. Okay, same pattern. Okay, as the red player gives more and more and more, his payoffs are going down. The other guys are going up. Got that idea? Okay, so that's the idea of developing this payoff matrix. And we look at it and we think, well, okay, now we've got the payoffs. What if we use our dominance reasoning? What are we going to come up with? Well, let's take our little X's and O's. Let's use the X for the blue player. If the red player keeps 4, what's the blue player's best response? Well, compare this 3. It's better to be over here at 325, better to be here at 350, better to be here at 375, better to be here at 4. So that's the best response of the blue player. So put a little X there, okay? What if the red player keeps 3? Well, 475 is better than 450, which is better than 425, better than 4, better than 375. So again, best response over here is to keep 4. And we can keep marching down this column because for everything that the red player does, the left-hand side over here is bigger than anything on the right-hand side. Okay? And that's the idea of dominance. No matter what the red player is doing, whether the red player is keeping everything, giving 1, giving 2, giving 3, giving 4, the blue player's best response, if they're only interested in their own payoff, okay, if they're only interested in their own payoff, is to keep everything himself. So this is a dominant strategy for the blue player. So put a little box around this, and notice we're trying to isolate the dominant strategy, and then these are the payoffs that the blue player is going to get in the dominant strategy. Notice that the payoffs that the blue player is going to get in the dominant strategy will depend upon what the red player does, okay? Because the more the red player gives, the better it is for the blue player. Let's do the same thing for reasoning in this dominance way for the red player. Well, supposing the blue player does its dominant strategy, which is what you'd expect it to do, keeping 4, what's best for the red player? If they're only interested in their own payoffs, 4 is better than 375, is better than this, better than that, and that. So we put this guy up here like this, okay? Now, again, every row in the top is going to be exactly the same. Now, I'm putting the knots in these boxes, but let's see what they mean. This knot here is saying, as I look down these numbers, going down this column, why am I going down the column? Well, I'm thinking about what if the blue player kept 2? What would my payoff be from keeping 4, keeping 3, keeping 2, keeping 1, keeping 0? Well, my best response, again, assuming I'm only interested in my payoff, is to keep 4. So this row, all of the best responses are in the same row, so keeping 4 is a dominant strategy for the red. Okay. Now, if you look at the noughts and crosses, there's one cell where the noughts and crosses, there's 2 noughts and crosses, and that's called a Nash equilibrium. This best response type analysis that I'm doing, we're putting in the noughts and crosses, wherever you find a pair of noughts and crosses, that will be a Nash equilibrium. Now, we're going to define that concept and look at it in a second. But here you want to think of 2 things. There's what are the strategies in this Nash equilibrium? Well, the strategies are for both players to keep everything, to give nothing away. Okay? What are the payoffs in that Nash equilibrium? They are 4 and 4 each. Okay, so distinguish between the strategies in the equilibrium or the payoffs in the equilibrium. Okay? Now, problem is down here on the right-hand side, here are these nice missed opportunities. And if you go back and look at the payoff matrix that we developed in class yesterday, basically I just had the 4 corners of this thing for you guys to work your way through and apply our dominant reasoning in, okay? So the fact that we kind of added more options for the players doesn't really change the game. I mean, it does change the game. There's more things they can do, but it doesn't change their dominant strategies or the payoffs in that equilibrium, okay? So here's this prisoner's dilemma. We got more options for the players. They could give a little bit, help out their neighbors, things like that. But as long as they're only interested in their own payoff, the best response for them is to keep all of the payoffs themselves. They don't put anything into the group account. No parks get built. And we miss out on these great mutually beneficial opportunities. And this idea sometimes is called free riding. There are great cooperative things that could happen, but it's in nobody's interest to contribute to them. Everybody free rides, and we get an outcome which is individually rational, but collectively it seems kind of a paradox, is that everybody could do better if they could somehow get away from this prisoner's dilemma. Okay? Now, the next graph, I didn't put on the overhead. You can have a download of it, but you don't really want to copy this thing down, okay? This is the result of some experiments that were done by a group of economists who are interested in trying to figure out how much people give when they can help out other people, okay? Now, so this is, the way this thing works is, on this axis here is the percentage of their endowment that people give away into the group account, okay? So if you give nothing, it's down here. If you give everything, it's up there, okay? Now, in this axis down here, what they would do is, we just had the one-shot game, okay? Where each player was playing once. Well, in these experiments, what happened is, each player plays against the same player 10 times. Or each player plays against another, an honest, randomly chosen player, 10 times. Or each player plays against someone else so they can identify a friend 10 times. Okay, so there's those kind of variations in the experiment. Another variation in the experiment they did was how many people are involved in this? We only had 2-player games. Some of these have sort of multiplayer games. So there may be 4 people, there might be 10 people, there might be 40 people. Okay, and the idea with contributing to the group account, when they say there's 40 people, is that if I put in $1 to the group account, then I can give, that group account's going to get multiplied by something, but in our case, I was able to give 75 cents to the blue player. I could give 75 cents to every player out there. Okay? Remember, not just, I'm only, if I put in $1, I'm only going to get 75 cents back, because I get to share in the common pool as well. But it's going to cost me, yet I'm going to lose. But at the same time, I could give everybody else in that pool 75 cents. Okay? So that's the idea of contributing to this big public good at a small cost to yourself. On the other hand, supposing that the rate of return wasn't too high, so I put in my $1, I can only give you 10 cents. Every one of you 10 cents. Okay? Then that's like a small rate of return. And they have this treatment variable looks at the rate of return on the group account. There's an acronym called MPCR. It's the marginal per capita return. In our case, it was 75 cents because we just had 2 players. And basically, if I gave up $1, okay, gross, I could get 75 cents into everybody's hand, including myself. So my net return was, I'm losing 25 cents. But if I give up $1, I can make an equal contribution of 75 cents for everybody. And then what they did is, in these experiments, they said, well, let's do the 75-cent one, let's do a 30-cent one. They did a couple of other treatments, and those are the results. Okay, it's like you're sort of looking at this and you're thinking, these are the average contributions in each of these different experiments, round by round, for a bunch of different experiments, and you're thinking, it's kind of crazy, isn't it? I mean, the graphs are all over the place. The red line on the bottom is what the theory predicts. If I chunk this up here like this, the theory says if people are only looking at their own payoff in all of these games, then the dominant strategy is for them to give nothing, every one of these games. We should be seeing everything along the red line. It doesn't matter whether it's the first period or the last period or whatever. Everything should follow along that red line. But it doesn't. Okay? It's kind of all over the map. And that's what was kind of a puzzle about these experiments. Like, well, what's going on in these experiments? How do we explain this? And so I put up a little, if you're interested, you don't have to be interested for the exam, but if you're interested in following this idea up, and if you're ever going to do any charitable contribution fundraising, you should go and read this stuff, because there's a lot of insights that are coming out of these experiments about how is it that you can get people to contribute to these public goods, these things which can benefit everybody, instead of running into the prisoner's dilemma. And there's a couple of things they think about. One is that what happens if the game is repeated, more than a one-shot kind of game? And if you take this turquoise line here, you can sort of see, well, it goes down, pops back up again, goes down, pops back up. But generally, it's kind of going down from left to right, okay? Or let's take the red guy. The red guys, at the very beginning, that experiment, they started off giving a lot, but it kind of tracks down, it pops back up, you know. But you might think, well, there's kind of a downward trend sort of here, so that as people repeat a game, as it gets repeated more and more, at the beginning they might be trying to signal to one another, well, let's get the goodies. And then as the game goes on, towards the end of the experiment, then they would do the individually rational thing of just trying to maximize their own payoff. Okay. Another thing is with experience. You know, inexperienced people over here, everybody's starting off giving something, and certainly for some of them, they track down. They seem to learn during the process of the game. The group size, well, people kind of thought it'd be hard, and for you know, it's easier for a group of 4 people to coordinate with one another than it is for a group of 10 or a group of 40. But oddly enough, some of these large amounts of giving still held for the larger groups, okay? And that's kind of nice in a way, because what you're saying there is that privately people face a cost to give to a large group, you know, and you think, well, how do you get this coordination going? Because there's huge payoffs out there for everybody else if they just give a little bit. And they did. Okay? They had a treatment called partners and strangers, where the idea is that, you know, I picked 2 students randomly so you don't know one another, but what if you kept playing with the same player? Maybe you'd kind of build up a relationship, even if you couldn't communicate with that player, build up a relationship with them. That's called a partners treatment. And sure enough, they found that there was more giving in those partners kind of treatments. And when we get to what's called evolutionary game theory towards the end of the course, that's one of the predictions that comes out of this repeated games in evolutionary game theory, that you have these repeated interactions where people can, you know, kind of develop a relationship, even if they don't communicate very well. All kinds of interesting cooperative things emerge, which you wouldn't predict would happen if it was only a one-shot game. Okay? So that's the kind of evidence that comes out. It really is all over the map. The theory says we should be down here, but actually what happens in these experiments is up here. Okay, now I want to move to another theory concept away from that voluntary contributions mechanism. When we looked at this payoff matrix here, we were doing some dominance reasoning, okay? What we are saying is that the red player here has a dominant strategy of keeping everything, because this strategy is better than the strategy of giving 1 if the blue player keeps 4, because 4 is bigger than 3.75. If the blue player keeps 3, because 475 is bigger than 450. If the blue player keeps 2, because 550 is better than 525. If the blue player keeps 1, 625 is better than $6. If the blue player keeps 0, because 7 is better than 675, okay? And so this strategy dominates that strategy. No matter what the blue player does, this is better for the red player, given these payoffs. It's also better than this strategy, because 4 is bigger than 3.5. 475 is bigger than 425. Okay? No matter which strategy you're comparing this one with, it dominates every other strategy. So that's called a dominant strategy. Okay? It's easier in the 2x2 games because there's only usually 2 strategies, right? But here, they've got 5 different strategies, and you have to check out, does this one dominate that? Yes. Does it dominate that? Yes. Does it dominate this one? Yes. Does it dominate this one? And how do you check that out? Well, you go down column by column and make the comparisons. So that's, on this next handout, that's what I've done, is I've set up a little kind of stylized element of a payoff matrix. So here, there's B strategy 1, B strategy 2, B strategy 3, B strategy 4. So these are the blue strategies. And here, the red strategies are A and B. And I put in dots for the blue player because the red player is focusing on his own strategy, his own payoffs. Okay? So you can use dots, you can cover them up. Use the colors to focus your attention on, okay, does A dominate B? 5 is lower than 6. Well, when B plays blue 1? Does B dominate A? Well, yes, because 6 is bigger than 5. When blue, sorry, let me say that again. Is B better than A1? Not dominant, because the dominance idea isn't just is the red B better than A? Well, yes, it is here, but it's also got to be better here, and it's got to be better there, and it's got to be better there. No matter what the other guy does, we got to have for dominance that this number is bigger than that number. A's payoff if he plays B is better than if he plays A. A's payoff if he plays B is better than if he plays A. A's payoff if he plays B is better than he plays A. A's payoff if he plays row B is better than if he plays row A. Okay? So no matter what the other guy does, B is always better. Okay? Now, notice that when you play your dominant strategy, your payoff is going to change depending upon what the other guy does. Like, there's some interaction here. What they do does affect you, but no matter what they do, you're always better playing B than you are A. Okay, and that's the dominance reasoning. There is a slightly different concept called weak dominance. If you look down here, let's look at this payoff matrix. Now, these numbers here, 5 and the 6, are the same here. 3 and 4 are the same. But I've changed these numbers, so I've got this 4 has increased from that red 3. Okay? So when we try the dominance reasoning, does B dominate A? Well, it's better here when B does strategy 1. It's better there when B does strategy 2. But it's the same when B does strategy 3. Okay? And then it's better here when B does strategy 4. So it's not strictly better all the time, but it's certainly no worse. Okay. Now that's another idea of dominance. If you're, when you're thinking about it, there's sort of an idea, I've got something that's better no matter what the other guy does. That's a really nice strategy to have. But it might be that the other guy can do various things, and some of the times it's not going to make any difference to me. Okay, I don't lose anything, but I don't gain anything. And the other times I do gain anything by playing B. Now that's called a weak dominance. Okay, so just when you're looking at payoff matrices and trying to figure out if they're dominant strategies, you can use either strict dominance or weak dominance. The strong or strict dominance is nicer in the sense of it means no matter what the other guy does, one strategy B is always better than the other one. With weak dominance, it's not always strictly better. Sometimes it's no worse, okay, or the same. Okay, so just keep that in mind. It turns out in some of the games that we'll look at, there will be equal payoffs where you'll be kind of indifferent. There isn't one best response or another best response, and we have to decide what are you going to do. And the other player has to figure out what are you going to do. And well, you might think if the blue player is trying to figure out what the red player is going to do here, you'd sort of say, well, yeah, red doesn't have a dominant strategy, but they got a weakly dominant strategy, so I'll expect them to play that one. Okay. Okay. Let's miss off this little section on the generals. I might come back to this idea of the looking at the prisoner's dilemma in a second, but or the general idea of the prisoner's dilemma. But I want to get on to a game that's different than the prisoner's dilemma. Okay, so we can't apply the dominance reasoning. And why can't we apply it? Well, this is a two-player game. In the text, it's described in these pages in the text, and it's a game against where the Reserve Bank or the monetary authority in the country might be interacting strategically with Parliament, which is deciding on expenditures. Okay, and basically it's a simplified, stylized kind of simultaneous game where the monetary authority can have low interest rates or high interest rates. The fiscal authorities in Parliament, they can have balanced budgets or budget deficits. Okay, now notice the pattern of the payoffs in this game. If you look at a situation where there's low interest rates and balanced budgets, that's the best for the monetary authorities. They're blue guys. They really like that. Okay, the fiscal guys, they like that pretty good. The number 3 is pretty high, but given the interest rates are low, they're going to be able to get more votes if they run these budget deficits, and they can improve their outcomes. Okay, so it would be better for them if they could have low interest rates and run budget deficits. But that's the worst situation for the monetary authorities. They don't like that. They don't like these guys running budgetary deficits because that's going to lead to inflation, and their idea is to control inflation, so that's bad. Okay, look at the other pattern of payoffs. Here, the worst situation for the fiscal guys, if they're running a budget balance and interest rates are high, both of those are bad for vote getting. Okay, whereas from the monetary authorities' standpoint, they like this budget balance stuff because they're really worried about inflation, so that's a pretty high priority for them, and it's this bad outcome for the fiscal guys. And then we have this second worst situation over here. So this is the game, monetary authorities versus the fiscal authorities. 2x2 simultaneous game. We want to try and make a prediction here. What's going to be the outcome of this game? Well, let's see if each player has a dominant strategy. Okay, look at the red player. If there are low interest rates, then running a budget balance isn't as good as running a budget deficit. If there are high interest rates, running a budget balance isn't as good as running a budget deficit. Okay? So the red player has a dominant strategy to run a budget deficit. So let's put a couple of little circles in here in these cells. That's the best responses of the role player. They've got a dominant strategy. No matter what the monetary authorities do, they're going to want to run a budget deficit. They don't want budget balances. Okay. What about the monetary authorities? Do they have a dominant strategy? Well, if there's a budget balance being run by the fiscal authorities, then they'd rather have low interest rates. But if these guys are going to keep on running budget deficits, then 2 is better than 1. They want high interest rates. Okay, so here's a game of strategic interaction where one player has a dominant strategy, the role player, but the blue player doesn't have a dominant strategy. Okay, so you're sort of thinking, it's a simultaneous game. Let's pretend everything. The beginning of the year, there's decisions that are taken whether interest rate is going to be high or low. The beginning of the year, there's going to be decisions about budget balance and budget deficit. What should the blue player expect? Well, the blue player should expect the red player to play their dominant strategy. Okay? It's not that they couldn't run a budget balance. It's just not a reasonable thing for them to expect. If they do expect that, their best response is to play a strategy which puts on high interest rates. Okay? The red player should expect the blue player to play high interest rates. Not because the blue player has a dominant strategy, but because they can anticipate that the blue player will be knowing that the red player has a dominant strategy, and would expect them to play that strategy, so they can expect the blue player to play the strategy of high interest rates, which isn't a dominant strategy for them, but it's a strategy they would play, expecting the dominant strategy to be played by the red players. So you see, get that idea of the layers of reasoning that go on in a simultaneous game. Nobody's observing what the other players are doing and making their choices. They're trying to think out what are we going to expect to happen. And so in this cell, we have what we would call an Nash equilibria. Let's put a little circle around it. I should have had this done before for you. Help. Okay, let's just put a little circle around this guy here. And this is what we would expect to have in the game. Okay, the red player would play, the blue player will play their high interest rate strategy. Budget deficits will be run, and we're stuck at a situation which is kind of like the prisoner's dilemma, right? If both players could somehow commit to having low interest rates and budget balances, then they'd both be better off. And this is the kind of strategic theory that's used in macro and monetary reasoning now, where they're trying to look at the interaction between the fiscal authorities and we don't have any private players here, like people who are buying houses or whatever, and the monetary authorities. And the idea is that we're stuck in this equilibrium of high interest rates and budget deficits when somehow if we could just change the game, we could both be better off. Now this isn't a prisoner's dilemma, and the reason it's not a prisoner's dilemma is the prisoner's dilemma has both players having a dominant strategy. Okay. Now, let me take one more payoff matrix, and let's have a quick look at this one. This is a 4x3. It's a two-player game, and forget about where the story is from where the payoff numbers come from. But we want to analyze this game, saying, let's imagine this strategic interaction. Could we find dominant strategies? Well, let's have a look. Would the red player have a dominant strategy? That is T better than H? Is T better than L? Is T better than B? Okay. And the idea is, well, supposing the blue player plays L, is 3 better than 4? Nah, it's not very good. Okay. It is better. T is better than L, but it's not better than 5. So when the blue player plays L, T isn't better than everything else. Is there anything that's better than everything else? Well, the red bottom strategy B has got a 5 when the other guy plays L, and that certainly beats any of these other numbers. So that's looking pretty good when the other guy plays L. But it's not so good when the blue player plays R. Because then there's only a 9, and 12 and 10 are better than 9. Okay, so T can't be a dominant strategy, B can't be a dominant strategy, and you can figure out, well, could L be a dominant strategy? It's looking pretty good here when the blue player plays R because you get a 12, but it's not looking so good here when the blue player plays an L because you get a 2 versus 4 or 5 or 3 or something else. Okay, so the red player doesn't have a dominant strategy. The blue player also does not have a dominant strategy. I'm just going to say that because we're running out of time, but go back and check it out. Okay, is any of these blue players' strategy best, no matter what the red player does? Now, so just take faith here. Then there are no dominant strategies. What about bad things, dominated strategies? And it turns out there is a dominated strategy. Okay, for the red player, compare strategy H with strategy B. Okay, 4 is less than 5. That is, when the blue player plays L, you get a better payoff playing row B than you do row H. When the blue player plays M, 4 is better than 3. When the blue player plays R, 9 is better than 6. Okay? Now, B isn't a dominant strategy because there are things that are better than B, like when, for example, if the blue player plays R, then either T or L is better than B, but H is dominated by B. It's kind of like, it's not the best thing. B isn't the best thing, but H is definitely a worse thing because there's something that's always better than it. Okay? So we want to eliminate that. And we'll put a line through it. Okay. Now what are we doing with eliminating it? We're eliminating our head. We don't expect it to happen. So the game changes. Now it's a bit of a smaller game, isn't it? It's really only once you sort of don't expect this strategy to be played, it becomes a 3-by-3 game. Now, if you look at the blue strategies here, I want you to notice something. The blue strategy L, where you get payoffs of 1, 2, and 6, is always worse than the blue strategy R. Okay, because 1 is less than 2, 2 is less than 3, 6 is less than 7. Okay, so we could say, aha! Once we've eliminated H from the red player, then the blue player does have a dominated strategy. But we couldn't have eliminated L in the first place for the blue player because as long as we think there's some possibility of H occurring, then L's not a bad strategy, okay? Because if H occurs, then it's a pretty good response to H to play L, if you expect H to occur. But we don't expect H to occur because we've eliminated it. And since we don't expect H to occur, we don't expect L to occur because L is dominated by R. Okay? So now we have even a smaller game. Okay, so this is a process of iteration, and it's elimination of some strategies, and the elimination of dominated strategies. So you get this long, wordy thing, successive elimination of dominated strategies. Okay? So what about this game? What can we do now? Well, let's have a look. Sorry, we don't need that. We're going to eliminate T and B. How are we going to do that? Well, look at L. L is a role player's strategy. If the blue player plays M, 5 beats 2, 5 beats 4. If the blue player plays R, 12 beats 10, 12 beats 9. Okay, so in this new game, which is the third iteration that we've done, and we're there because we don't expect H to be played, we don't expect L to be played, because we've already worked out that neither player would find those advantageous if they've gone through the sequence of reasoning, we can eliminate those two. Having eliminated those two, what do we expect to happen? Okay, well, we look at the blue 4 is bigger than the blue 3, so we can eliminate R, because there's no point in playing R, given that we've eliminated everything else to play, and we're left with this. Okay. Now, that particular strategy is kind of the end result of a sequence of eliminating things we don't expect to happen. Now, sometimes this is another way that you can think of deeply or intelligently about strategic reasoning. You say, there's nothing I can't say for sure that there's a best strategy for me or a best strategy for somebody else. But as I think about the game and as they think about the game, there are definite things that are bad for me. There are definite things that are bad for one of us. I eliminate those. Then I look at the whole situation again, and I see, are there definite things that are there any dominant strategies? Or are there any dominated strategies? Okay? And you go through this sequence, and lo and behold, we came up with a prediction that in this game, the blue player would play M, the red player would play L, and we would end up with payoffs of 5 and 4. Now, notice nobody is observing this. The idea is just to kind of rationally, intelligently, and deeply think through what it is that's reasonable to expect other players to play. And we end up with a pair of strategies and a pair of payoffs. That also turns out to be a Nash equilibrium, which we'll talk about more in the next class on Monday. Okay?